Hello everyone, welcome to the channel. In this video, we're going to focus on evapotranspiration and crop water stress monitoring using MODIS dataset in Google Earth Engine. Now let's get started. We're going to focus on this topic on evapotranspiration and crop water stress monitoring using MODIS dataset. What is evapotranspiration? Evapotranspiration is the process by which the water is lost from the Earth's surface to the atmosphere through the evaporation from soil and water bodies and transpiration from plants. It's a critical component of hydrological cycle and plays a significant role in regulating climate and water availability. Next, crop water stress. When the amount of water available to the crop is insufficient to meet its demand for the growth and development, it is experiencing a crop water stress. This can have a significant negative impact on crop yield, quality and overall health. The factors contributing to the crop water stress, the insufficient precipitation, the lack of rainfall can lead to water deficits in soil, the high temperature. The high temperature increases the rate of evapotranspiration, leading to a greater water loss, and followed by the poor soil drainage. Poorly drained soil can limit the water infiltration and availability to the plants. And salinity. The high level of salt in soil can reduce the water uptake by the plants. And last, over irrigation. Excessive irrigation can lead to waterlogging and nutrient leaching and also affecting the plant growth. Now I'm going to get back to my Earth Engine. To estimate the evapotranspiration and crop water stress monitoring for any study region, first we have to define our region of interest. To define a region of interest, we are going to use a point data to specify our region of interest. To define a point data, we define this variable called a location coordinate. We're going to specify the latitude and longitude of the study area. For example, you can able to see this particular point data which is placed on this particular country, that is Thailand. You can place your point data. Let me delete this particular one here. Now to place a point data, we're going to navigate to this option called add a marker, and I'm going to place my point data over the HydroSHED basin of my choice. First let us import a HydroSHED basin into our Earth Engine. To do that, first I have defined this variable point of interest. To convert to this particular point into a feature, I have defined variable point of interest equals to earthengine.geometry.point, the location coordinate which refers to the latitude and longitude. And next we're going to add our HydroSHED basin into Earth Engine. This is the dataset we're going to use. This is the HydroSHED basin level 5 dataset here. Using this particular script, you can able to access this particular HydroSHED level 5 datasets. Paste my this particular code here to access the HydroSHED level 5 dataset. To visualize all the level 5 basins, I've defined this map.addLayer basin with the default visualization parameter and have output the layer name as a basin here. I'm going to run this code. Now in the layer section, I'm going to click this particular layer called Basin. Now you can able to visualize. We have the variety of all the basins of HydroSHED. You can able to see that. In that, I'm going to choose a specific basin here. For example, I'm going to select this particular basin. For that, I'm going to click this option called add a marker, and I'm going to place a marker over this particular area. I'm going to place my marker over this particular study region, that is this particular HydroSHED basin. Now we have the latitude and longitude generated for this particular point data here. I'm going to click this option called show the generated code. In that, you can able to visualize we have the latitude and longitude of this particular point. I'm going to copy this particular latitude and longitude, and I'm going to paste it here in the location coordinate variable here. You can just use your Control V to paste this particular coordinate in this variable. We are using this point data to select this particular HydroSHED basin. To perform our evapotranspiration and crop water stress monitoring. For that, we are using this set of scripts here. Next, again, I'm going to load the HydroSHED basin dataset here in order to filter this particular basin out from this HydroSHED basin. From all this dataset, I'm going to filter this particular basin. To do that, I have defined this variable called ROI basin, that is of region of interest. Our region of interest is this particular basin here. This is our region of interest, this particular basin. I'm going to filter this particular basin out. For that, define this variable called ROI basin equals to earthengine.featureCollection, and this is the code for the HydroSHED WWF HydroSHED V1 basin high base 5. So now to filter this particular basin, we define dot filter bound point of interest. So the point of interest refers to this particular variable where we have specified our point data to filter this particular basin. So next, to add this layer, we define that map.addLayer ROI basin with the default visualization parameter and output the layer as basin ROI. That is our basin region of interest. And to center this particular layer, we define map.centerObject ROI with a zoom level of 6. So next, we're gonna load our MODIS Evapotranspiration and potential evapotranspiration dataset into Earth Engine. So to do that, I've defined this set of variables here. So let me explain about this particular dataset. So this is the dataset where we're gonna use, that is TerraNet Evapotranspiration 8-day global 500-meter resolution. So these are the description about this particular band here. So evapotranspiration latent heat flux product is a 8-day composite product produced at 500-meter pixel resolution. The algorithm used for this MODIS 16 data product collection is based on the Benman's equation, which includes an input of daily meteorological reanalysis data along the MODIS remotely sensed data products such as the vegetation, property dynamics, albedo, and land cover. So let us take a look at the variety of band that is available in this dataset here. So total there is around 4 different bands available. The ET refers to total evapotranspiration, and LE refers to average latent heat flux, and PET, which refers to total potential evapotranspiration, and PLE, which refers to average potential latent heat flux. So in this band, we're gonna use this two set of this particular band here, that is ET, total evapotranspiration, and PET, that is total potential evapotranspiration. These are the following two bands we're gonna use. So that is the unit for this particular band here. You can able to see here kg meter square per 8 days, and similarly the PET is as a kg meter square 8 days. So this is the unit for this particular band. So now let me get back to the Earth Engine here. So before proceeding towards our MODIS evapotranspiration and potential evapotranspiration, let me show you the layer we have generated. So we have managed to filter out this particular basin. So that is this particular watershed basin. So you can able to see that, which is given in black color. So now let us proceed towards MODIS evapotranspiration. So we're going to perform the analysis from 2001 to 2024. So this particular dataset availability is from 2001 to 2024. So the analysis, we're going to start from 2001 to 2024. So we're going to load this data. For that, we define variable MODIS ET collection equals to Earth Engine.image collection MODIS 06 MOD1 16 A2 GF. This is the code to access this particular dataset, and from that we're gonna select the two bands. So in this particular dataset, we have around 4 different bands that is available, and in that we're gonna select this total evapotranspiration and the potential evapotranspiration. To select these two bands, we had referred dot select ET and PET, and we're gonna filter with the specific timeline starting from 2001 to 2002. So for that, we define this variable start date and end date is equals to 24. So to filter the specific timeline, we define dot filter date, start date, and end date. So we filter the dataset for this specific date range from 2001 to 2024. So next, to calculate the mean evapotranspiration over the entire period. So to calculate the mean evapotranspiration over the entire period, we define this variable called mean ET equals to MODIS ET collection dot select. So we are selecting the total evapotranspiration. So ET here refers to total evapotranspiration. Let me show you that. So you can able to see the ET here refers to total evapotranspiration, and it has a scale factor of 0.1. So to calculate the mean evapotranspiration, we defined dot mean function, and to apply the scale factor, we are defined dot multiply 0.1. So this is the scale factor we have to apply for this particular dataset. So to convert to it to correct units, and we are applying the scaling factor because in order to have ET value in a correct range of value, we need to apply the specific scale factor. And now to visualize this particular layer, we defined map.addLayer mean ET dot clip referring to our ROI basin, that is this particular basin. So you can able to see this. This is our study area. This is the basin, and we are referring to that. So dot clip ROI basin, and we are setting a minimum value of 0 and to a maximum value of 100. And the following, we are using this set of color palettes. We introduce this set of color palettes. So blue, green, yellow, and red. So the blue which indicates the lowest ET value, and the red which indicates the highest ET value, which is indicated in this set of color starting from blue, green, yellow and red, and output the layer as mean ET 2001 to 2024. So now to visualize this particular result, we're gonna click this option called run, and now let us visualize the result. I'm gonna navigate to the layer section here, and we're gonna click this layer called mean ET. So now here you can able to visualize here. So this is our study region. Let me turn off this particular layer. So now you can able to view it more clearly. So you can able to view from this particular image. With starting color we are referred that as we are starting from the blue color. So blue which refers to the lowest evapotranspiration. So from this image you can able to see the central part of this particular study region has the lowest evapotranspiration. So the green which indicates more like moderate level of ET here. So moderate level of evapotranspiration which are indicated in towards this part of the study region here. You can able to visualize it, and in the central and towards the southern part of the study area has the lowest ET value, and you can able to find that mostly this particular study region has the ET value that is from the lowest ET value is being observed in the towards the southern part, and also moderate ET value is being observed towards the northern part of the study region. And this particular study region has a lot of vegetation here. You can I have turned on this satellite mode here. I gotta turn this off. So now you can able to visualize it more clearly. So this is our region of interest, that is the watershed basin, and this is the mean ET value. You can able to observe this particular set of section here has the lowest ET value, so which indicates that this particular area has a lower vegetation content here compared to this part, the southern part of the area comparatively has a higher vegetation. So next we're going to navigate to, and also you can observe the evapotranspiration value here in this particular layer mean ET. I'm going to click this option here, and now here you can able to observe. So you can able to see the range start from 0 to 100. The ET values, and the lowest starting from 0 and the highest is around 100. You can also check this options here, that is the custom options. You can use this variety of this different stretch options to view the image. So we're gonna apply the stretch 90%, and we're gonna visualize it now. So now when the stretch 90% has a ET value starting from 17.26 to 30.45, and I'm gonna apply it. So now here you can able to visualize it here. So you can observe this contrast of color here. So we have this ET value starting from 17.26 to 30.45. So in this particular stretch of 90%, you can able to view the different classes more clearly here, the ET values. So based on the color code here, we are starting from blue to red. So range is from 17 to 30. So the blue which indicates the lowest value of ET, which is in this central part and towards the southern part of the study region, and the highest ET that is observed, that is 30.45 kg meter square of ET. So that is observed in the red areas. You can able to observe that is towards the northern part of the study region. So and also towards the eastern part of the study region, you can able to observe it. So next let us calculate the mean ET for summer season. For example, we're gonna focus on this particular set of months here, the June, July and August. So to do that, we define this variable called summer ET equals to MODIS ET collection dot select ET. We're gonna select again this particular band, that is total evapotranspiration. Now we're gonna filter with this for the specific set of months here, starting from June, July to August. So to do that, we define dot filter earth engine dot filter dot calendar range, starting from June to August, and the unit is a month. And so we're gonna calculate the ET during this set of months here, starting from June to August. So next we're gonna to calculate the mean ET value for this month. We define dot mean function, and we're gonna multiply with the scale factor to convert to correct units. We're gonna apply this particular scaling factor dot multiply 0.1. So this particular scale factor is given in the dataset here. You can able to see that. So next to add this layer into earth engine, we define map.addLayer summer ET.clip ROI basin, referring to this particular basin. and we are setting a minimum value of 0 and to a maximum value of 100, and the color palettes we are going to use this particular is blue, green, yellow and red, and output the layer as summer evapotranspiration. So now let us visualize the result here. We're going to visualize the summer total evapotranspiration layer here. So we're going to navigate to this option in the layers section here, and I'm going to click this particular layer called summer 80. So it's going to load it. So now here you can able to visualize this summer 80 here. So it is loading the layer. I'm going to wait for a few seconds. So now this is our summer total evapotranspiration for the month starting from June, July and August. So we're going to navigate to the layer here. I'm going to click this layer called summer 80, and in that you can able to see the range start from 0 to 100. So we have defined the minimum and maximum value. So we're going to apply this custom option. We're going to click the stretch 90%. So it's going to load and we have to wait for it. Yeah, it's loaded. So now the range starting from 22.96 to 37.6. This is a range during the summer season for the specific study region from June, July and August. 22.69 to 37.60, and I'm going to apply it. So it's loading the data. So it's loading here. You can able to see that. So once you did that, I'm going to close this. So this is the summer. So in the summer ET evapotranspiration. So we have again this particular study region has has the lowest ET. Because of vegetation comparatively, this particular study area in this region, the vegetation is comparatively lower. In other part of the study region in the northern has a higher vegetation compared towards the southern part of the areas. And similarly, the red area which indicates the highest ET value, there is around 32.60 kg meter square of ET evapotranspiration. And now in the summer, during the summer, so you can able to see this value here. So we have the green values which indicates a moderate level of ET value which is observed. Comparatively, in case of previous our mean ET value, you can able to observe the difference here. So you can able to view the difference during the summer season. Summer we have the lower ET in this part of the region, but in the central towards northern has a higher. But comparatively, the mean ET for entire period from 2001 to 2024 has this particular towards the northern part of the high areas has the higher ET values. So now let me navigate to the other section, other part. So next we're gonna export this particular ET, that is total evapotranspiration, to our Google Drive. So now to export this mean evapotranspiration image to drive, we define export.image.to-drive image mean et.clip ROI basin. So we are referring to our particular HydroSHED basin here, and description mean ET from 2001 to 2024. So the region is this particular HydroSHED, that is ROI basin. So the spatial resolution of this particular dataset is 500 meters. So we defined as 500. And the coordinate reference system, we are referring to mean et.projection coordinate reference system get info. And the maximum pixel values, we define this particular value here, and the folder we're going to specify is the evapotranspiration analysis. So next we're going to compute the crop water stress index using this following equation. So to obtain the crop water stress index, to obtain that we define equals to 1 minus total evapotranspiration divided by total potential evapotranspiration. So to obtain crop water stress index, we have to use this formula 1 minus ET divided by PET, that is of total potential evapotranspiration. So to compute the crop water stress index, we define this variable called crop water stress, that is CWSI collection equals to, referring to a MODIS dataset, MODIS ET collection dot map function image. So we're going to create a loop here. So in that we're going to define this variable called CWSI equation equals to image dot expression. So in the expression we are applying this formula here, that is 1 minus total evapotranspiration divided by total potential evapotranspiration. So we are applying this particular formula, that is 1 minus ET divided by PET, to calculate the crop water stress index. So next we're going to use this particular band, that is ET. We refer as the ET as the image dot select ET band, and we're going to apply the scale factor dot multiply 0.1. And similarly, we're going to refer this particular name, that is pet here, pet, that is image dot select pet, that is the total potential evapotranspiration, and we're going to apply, this is the band to total potential evapotranspiration, and we're going to apply the scale factor dot multiply 0.1. So now the equation is completed. So we have specified this variable et and pet here, so to compute this particular formula. So next we have to return, so we're going to return the equation by return CWSI equation dot, we're going to rename as CWSI, that is crop water stress index, and we specified as a dot copy properties, property of the image, the property of the input images copy to the output is the, so from the input images we need to copy the important characteristics for the time series analysis, that is the system time start and the system time end. We are specifying this particular is to retain its time properties to our image. So next we're going to calculate the mean CWSI, that is crop water stress index across the time period from 2001 to 2024. So we're going to calculate the mean crop water stress index. So to do that, we define this variable called mean CWSI equals to CWSI collection, referring to this particular variable here, CWSI collections, and we're going to specify a dot mean function in order to obtain the mean crop water stress index image. So for that we define this particular function called dot mean function, and next we're going to add this layer for visualization. So to do that we define map.addLayer mean CWSI dot clip ROI basin. So we are referring to our study region, and this is the image we're going to generate for our the mean crop water stress index from 2001 to 2024. For that we define this particular variable, and we're going to specify the minimum and maximum value. We specify the minimum of 0 and a maximum value of 1. So these are the following set of color palettes we're going to use, that is green, yellow and red, and output the layer name as mean CWSI. So now to visualize the result, we're going to click this option called run, and now we're going to navigate to the layer, and I'm going to click this option called mean CWSI crop water stress index. So it's going to load the layer. So now here you can able to visualize, we are visualizing the crop water stress index for the specific study region. So we have given the set of colors starting from green, yellow and red. So green, which indicates the lowest crop water stress index, and the yellow, which indicates the moderate level of crop water stress, and red, which indicates the highest level of crop water stress. So generally this particular set of value that ranges from 0 to 1. So 1 which indicates the highest level of stress, and 0 which indicates the lowest level of stress, and similarly the color which indicates here red, which indicates the highest level of stress, and green, which indicates the lowest level of stress, and yellow, which indicates the moderate. So from this image you can able to see from here the green, which indicates the lowest level of stress, and yellow, which indicates a moderate level of water stress, and in the center part of the study region, which indicated in red color, which indicates the highest level of water stress being observed in this areas, which is highlighted in this particular image, that is crop water stress index. So next we're going to navigate to this, we're going to load our land cover dataset and select the crop areas. So let me explain why we are using the MODIS land cover dataset and select the crop area. So because so from the image it is very hard to see the cropland region. So the CWSI, that is crop water stress index, is only suitable for the cropland region. So the CWSI value is not important for the value for the water class, that is the water pixels, and only the cropland is matters here. So you can remove all the non-crop region or the non-vegetation pixels through using the MODIS land cover dataset here. So for that we are using this particular dataset, MODIS land cover dataset. So basically we're going to use the MODIS dataset. We're going to remove all the land covers except the vegetation cover and the cropland class. And specifically the cropland is my target for this specific analysis. So this is our MODIS land cover type early global 500 meter resolution. So the dataset availability is from 2001 to 2023, and you can be able to see from this option here in the band section. So the resolution of this particular dataset is around 500 meters. These are the following bands that is available in our MODIS dataset. So in that, we're gonna specifically use this particular band, that is LC type 1. So we're gonna use this particular band. So this particular band contains following this classes, following different land use classes. So from here you can able to see that we have this particular class called cropland. So this is our focus of the study here. So we're gonna focus on this particular class, croplands. So you can able to see that, so which represents at least 60% of the area is cultivated cropland. So this particular class represents the cropland. So now we're gonna load our MODIS land cover data. For that we define this variable called land cover equals to earth engine dot image collection MODIS 061 MCD12Q1. So this is a code which we can able to insert the MODIS land cover data into earth engine. So next we're gonna select specifically this particular band, that is LC type 1 band. So to do that we define dot select LC type 1. So we are selecting this particular band containing the cropland class. So for that we are using this particular band called LC type 1. And next we are specifying this particular function called dot mode function here. So we are specifying this particular functions to get the most common land cover types. So for that we are using this particular function. So next we're going to define as a variable called cropland. So we define this variable called crop area in order to select this particular class, that is class 12, which represents the cropland. Let me show you that. So this is a LC type 1 band, and this particular the class 12 which contains the cropland class here. So for that we are mentioning this particular value equals to 12. So we are mentioning variable cropland equals to the land cover referring to the variable dot equal 12. We are selecting the croplands. So next to add this layer we define map.add layer crop area dot clip ROI basin. We are referring to a study region, and the color palette we are giving is a green color, and output the layer name as crop areas. So now let us visualize this layer here. We're gonna navigate to the layers section and we're gonna click this option called crop areas. So we're gonna turn this off. So we're gonna navigate to this particular section here, and let me make some changes to the visualization here. So we have two range, that is 0 and 1, and I'm gonna add the custom, I'm gonna add stretch 90% and apply. So we are getting kind of one color here. Let me add one more color here. I'm gonna add a red color. I'm gonna click OK and apply. So now we can able to see the difference here. So you can able to see that. So all the crop areas are highlighted in the green color, and all the non-crop areas are indicated in red color. From this image you can able to see that. Let me close this. So in this way you can able to visualize all the cropland versus the non-crop land areas in this particular study region. So, and also let me show you one more thing here. So you can also currently are visualizing in this in the color palette option here. You can also click this in the gamma mode, and you can just set your custom to. So in the single band option here you can set the range and stretch type, and you can apply it, and you can able to visualize here. So all the white area which indicates the non-crop areas, and the black which indicates the crop areas. So now let me close this. So we're gonna navigate to the other, we're gonna mask this particular crop water stress index to show only the crop areas. So using the land cover data we have managed to find the class 12, which is of cropland, and using that particular class we're gonna mask out the non-cropland areas. So to do that, to mask the crop water stress index to show only the crop areas, for that we defined variable called CWSI for crops equals to, that is crop water stress index for crop equals to mean CWSI. So which is referring to this particular variable, that is to calculate the mean CWSI value across this time period from 2001 to 2024. So we are using this variable, and in that dot update mask cropland area. So we are mentioning this particular class which represents the cropland. and we defined as dot update mask crop area. So it's going to filter CW, that is crop water stress index image data, to display only the cropland areas using our land cover data. So next, to add this layer in Earth Engine, we define map.addLayer CWSI for crops.clip. ROI Basin refers to a study area, and we are setting a minimum of 0 and a maximum of 1. And color palettes, we are setting this following color palettes, and output the layer as CWSI for crops. So now to visualize, we're going to click this option called run, and we're going to visualize the result. So we're going to navigate to this option here, layer, and we're going to turn on this layer. I'm going to turn off this layer here, and others are going to turn off other layers. So now here you can able to visualize, we have managed to mask only the crop areas here. So we can currently able to visualize only the crop area. We have managed to mask all the non-crop areas in the study region. So all the yellow color which represents the crop area in this particular study region. So you can able to observe here, currently we are set to 3 different color tones here. So 0 which indicates, so here the 0 which indicates the non-cropland areas, and the 1 which indicates the cropland areas. So you can also visualize in the gamma tone here, and let me apply it and let us take the look what it's going to give. So now it's loading it, so you can able to see that. So it's loading here. So let me turn to a map mode here, so you can able to visualize it more clearly. So now here you can able to visualize it more clearly. All the cropland areas are clearly highlighted here. And now we're going to make some changes to the custom option here. I'm going to click to 90% stretch, and once it's loaded here, I'm going to apply it. So now we're going to apply and visualize the range here. The range starts from 0.3 to 0.5, and from the image you can able to visualize it now here. That is the image, that is a image with the higher value, that is the white pixel area, which indicates the higher crop water stress index, that is in these regions which experience high crop water stress, so which is clearly highlighted in this brighter pixels here, and comparatively in darker areas which indicates the lower crop water stress. And this particular image is an average of 2001 to 2024 image. So from 2001 to 2024 based image this is. So in that you can able to see that this is the areas which indicates the high crop water stress, comparatively the darker areas which has a lower crop water stress. So let me close this, and at last we have to navigate the constant section here. So in the task section, so we have this unsubmitted task called mean evapotranspiration from 2001 to 2024. So this is the mean image for the total evapotranspiration from this years, that is from 2001 to 2024. So to export this particular image to your Google Drive, so I've clicked this option called run, and the window pop-up saying initiate image export. So the coordinate reference system, the scale, and to the drive, folders, evapotranspiration analysis, file name, and file format. So once you did that, we're gonna leave it rest to the default and click this option run to export the image to your Google Drive. So I'm gonna cancel this. You can export this particular image by clicking this option called run, and it will be automatically exported to your Google Drive once this appears to be in blue in color. So in this video, I have shown you how to calculate the evapotranspiration and crop water stress monitoring using the MODIS dataset in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like.